So today we're going to do a centrifugal pump design point calculation. So we'll read through this problem statement, talk about the diagram, and get started. So the centrifugal pump impeller shown has a width B of 8 centimeters at the inlet and 4 centimeters at the outlet. So realize this diagram here is showing us the impeller. So the small circle in the middle is the inlet. The water is coming perpendicular to the screen, entering the impeller, turning 90 degrees, and traveling radially along the impeller blades, and then coming out the outlet, which is the outer circle. So for clarity, only a single impeller blade is shown. So you see that impeller blade right here. This curved line is the impeller blade. In reality, there would be a whole bunch of those all the way around the impeller. So we see that the inner radius is 10 centimeters and the outer radius is 30 centimeters. Also in the problem statement, it tells us the depth of the impeller, or the width perpendicular to the screen, is 8 centimeters at the inlet here and 4 centimeters at the exit. So what we're asked to find here is determine the theoretical power, head, and flow rate. So realize we're doing a so-called design point calculation here, and that means that we're working at 100% efficiency. So everything here is frictionless. Everything's working perfectly. We're at the best efficiency point for this particular design of pump impeller. And I'll be talking about that at various points throughout the solution. Now the other thing we're asked for here is the magnitude and direction of the water velocity just as it leaves the impeller with respect to a stationary observer. So the point we're interested in there is right here. As the water leaves the impeller, what is its magnitude and direction relative to a stationary observer, not relative to the rotating impeller. All right, and also the water density is given there, 998 kilograms per cubic meter. So as I said, this is a design point calculation. So for the design point calculation, we have an equation that tells us the head produced by this pump as a function of its rotational speed. So the omega squared is its rotational speed. The acceleration due to gravity, g, is also in there. And then everything else in that equation are geometrical parameters of the impeller. So we have the inner and outer radiuses, R1, R2. We have the inner and outer depths of the impeller, B1 and B2. And we have the two angles that the impeller blade makes, beta 1 and beta 2. And all of those geometrical pieces of information are available either on the diagram or in the problem statement. So really, it's just a matter of taking those and plugging them into this equation to get the head that is developed by this pump. Now, I want to say a few words before I do that about where that equation came from. So there's a link in the description below to the lectures that develop this equation. And as I said earlier, it's a design point calculation. So a design point calculation for a centrifugal pump is concerned with the ideal performance of the pump. So the pump is operating at its best efficiency point, so 100% efficient essentially, and that's why this asked for the theoretical power, head, and flow rate, all right? Now, so again, if you want to know the details of where that equation came from, that's available in the link in the description below. But basically where it comes from is applying conservation of angular momentum to a control volume that includes the impeller and making quite a few assumptions along the way. We'll list these assumptions when we're done the problem just so we have a record of it, but we're assuming frictionless flow, steady state conditions, incompressible flow, isothermal flow, no heat transfer with the surroundings, and the flow entering and leaving the impeller is uniform, meaning that it doesn't vary with position around those two circles. Now, the other important assumption, or the important condition that has to be true in order to come up with that equation, is that as the flow enters the impeller, it's traveling purely in the radial direction. So that's called pure radial inflow. And that's sort of the optimum condition for a centrifugal pump to be operating in, produces the least losses as the water enters the impeller. We're going to be talking more about that as we get into the solution. But for now, we're going to go ahead and solve for the head that the pump produces by filling in this equation. So the head produced by this pump is going to be equal to, first of all, we have the angular speed. So that was given as 2400 RPM. In order for this equation to work, that needs to be in radians per second. So I need to multiply that by 2 pi over 60. So all of that gives me that angular speed in radians per second. So I'll give that units 1 over seconds, and then square the entire thing. So that's the omega squared. R2 for this impeller was 0.3 meters. So that's our R2, then divided by G, 9.81 meters per second squared. And then all that's multiplied by R2 again. So 0.3 meters, that's the outer radius of the impeller, minus R1, which is 0.1 meter, and that's squared. So that's our R1 squared divided by R2, which is 0.3 again. And in the denominator is also B2, which was 4 centimeters, 0.04 meters. And then B1 in the numerator is 0.08 meters. And then we need to multiply all of that by the tangent of beta 1 and the cotangent of beta 2. So I'm out of room on the end here, so I'm going to put that down here. So tangent beta 1, if we look back at the diagram, beta 1 is 45 degrees, and then the cotangent of beta 2, and beta 2 is 30 degrees. So calculating all of that out gives us an H value, so the head produced by the pump, of 356.45 meters. So that's the head that this pump will produce. Again, operating at its best efficiency point, which, because this is a theoretical maximum calculation, is an efficiency of 100%. So that's the pump head. The next thing we'll do is calculate the flow rate that this pump is going to provide. So the equation we have available to calculate the flow rate for design point calculation is shown here. So our volume flow rate Q is just related to geometrical properties of the impeller. So we have the inner radius, R1, the inner depth, B1, the inner angle, beta 1. So all of those things are taken at the inlet radius, and then the angular velocity, omega, is also in there. So again, it's just a matter of taking the numbers that we have in the problem statement and putting them in there and calculating Q. But I want to say a little bit about this equation just to give you a better feel for where it comes from. Again, take a look at the lecture video in the link below to see the detailed development of that equation. But I want to just sort of talk about it a little bit here. So we know that a volume flow rate is a product of a velocity times an area, right? So we can equate this equation, if we want, to V1A1. So the subscript 1 here refers to the inlet to our control volume, which is the water flowing across this circle. So across the circle into the impeller. That's what the subscript 1 means. So first of all, we see the area of 1. So remember, we're assuming uniform flow here. So the velocity entering the impeller is the same everywhere. Also, we're assuming pure radial inflow, and we'll get to that in a moment. So first of all, this area. Well, realize that 2 pi r is the circumference of that circle, multiplied by B1 will be the area. So 2 pi r B1 is the area. Now we have an extra r there, but that extra r times omega is the angular speed of a point on that inner circle. So that's how fast the impeller is moving at its inlet. So realize that the V1 in our equation then is r omega times the tangent of beta 1. So I want to just take a look at that in a little more detail and see where that comes from. So I'm going to draw on this thing. So let's say this is our inner circle, and the point I want to consider is immediately above the origin here, or immediately above the axis of rotation. So that spot right there, I'm going to draw it. So realize that point right there is moving to the right at a speed r1 omega, right? Because the whole thing's rotating at an angular speed omega, distance from the origin is r1. So that point on the impeller is moving in that direction, r1 omega. Well, the velocity of the water entering the impeller relative to somebody stationary on the ground is in this direction. And I'll just call that V. So this goes back to the design point calculation. For the design point calculation, the water enters the impeller perpendicular to that circle. In other words, pure radial inflow. That water is coming in like that. It's not coming in at an angle like that or like that. It's purely flowing in the radial direction. So that's the design point condition, part of that maximum efficiency operating point that we're looking at. So realize that there is an impeller blade here that water needs to engage with. And in this particular problem, that angle there is 45 degrees. So again, for maximum efficiency, the water has to be traveling tangent to that impeller blade relative to the impeller. So the velocity of the impeller blade is r1 omega in that direction. The velocity of the water relative to a stationary observer is perpendicular to the circle, so that's in that direction, and that's our V1. And the velocity of the water relative to the impeller blade has to be in the direction of this impeller blade. In other words, tangent to this impeller, which is at 45 degrees. So we know this angle here is 45 degrees. So I can make a little triangle here. So that's going to be r omega as well. So this is our absolute velocity, velocity relative to the blade, and velocity of the blade relative to the ground. So this is a 45-degree angle as well. So this means that V1 is going to be equal to R1 omega times the tangent of beta 1, right? And that's what we have in our original equation for Q. Our velocity entering is R1 omega times the tangent of beta 1. So that's just a little aside, actually, about an explanation of where that equation comes from. But again, for full details, look at the lecture video in the link below. So now we can substitute numbers into our equation for the volume flow rate. So Q will be equal to 2 pi R1 squared, and that's our 0.1 meters, the inner radius squared. The depth of the impeller at the inlet, so that's our 8 centimeters. The angular speed, that's our 2400 RPM. And finally, the tangent of 45 degrees. So all of that gives us a volume flow rate equal to 1.2633, and that'll be meters cubed per second. So using basic SI units everywhere, that volume flow rate will come out to 1.263 meters cubed per second. So we have the head that this pump produces and the volume flow rate through the pump. So the next thing we need to do is calculate the power requirements for this pump. So the so-called brake horsepower for this pump, which is the same as the water horsepower because it's 100% efficient in this theoretical calculation. Remember that this is the pressure increase across the pump times the volume flow rate through the pump. So the pressure increase will be rho GH, where H is the head that we just calculated a moment ago, and then the volume flow rate Q that we just calculated. So we know all of these things, so getting this power, we can go to that straight away. So our density, remember, is 998 kilograms per meter cubed. G, 9.81 meters per second squared. The head that we calculated a moment ago was 356.45. That's meters. And then finally, the volume flow rate we just calculated, which was 1.2633, and that was meters cubed per second. And so all of that gives us a power requirement, so the brake horsepower of 4.4087 megawatts. Okay? So again, standard SI units everywhere, so the calculation would come out in watts, but it was 4.4087, 10 to the 6th, so I just wrote that as megawatts. So that's the power requirements for this pump. So we've calculated the head, the flow, and the power required by the pump. The last thing this question wanted us to do was calculate the velocity of the water as it leaves the impeller blade at the exit. So we'll do that now. So to calculate the velocity at the exit, we need to draw a vector diagram at the exit. So this is the outer diameter of that impeller. The spot that I'm going to focus on is right here at the top. So remember, there's water leaving everywhere along that arc, but we're going to take a look specifically at the water leaving right at that point. So remember that the impeller itself is traveling in this direction because it's rotating in the clockwise direction here at a speed of R2 omega. So remember, we're working on the outer edge here. The impeller at this point looks like that. And this angle right here is 30 degrees. So realize the water leaves the impeller relative to the blade, tangent to that. So relative to the blade, the velocity of the water looks like that. So that's V relative to. Again, the subscript 2 means I'm working at the exit here. So V relative to and the radius 2. So the subscript 2 means we're at the outlet. So that's the velocity of the water relative to the blade, and this is the velocity of the blade itself. So we can just make a little parallelogram here so that we can illustrate the velocity of the water relative to the ground. So we're adding those vectors up, and that will be our V2. And that's what we're trying to find. So we want to know that velocity vector. So it's chopped off here, sorry, but there's a dotted line right along the top here. So that's our velocity vector that we're after. And I'm going to label this angle here as alpha, because we were asked to describe that velocity both in terms of its magnitude, which we'll get here in a moment, but also the angle that it makes with the outer diameter of the impeller. So in this little sketch, that would be the angle alpha. So that's what we need to figure out, is that velocity's magnitude and its direction in terms of this alpha, remembering that this angle here is 30 degrees, all right? And of course, we also know R2 omega. Now, what we want to do in order to figure out that velocity is draw another triangle here, drop straight down from that point, perpendicular to our R omega. Now, this component of V2, if I were to show this as a velocity component, realize that component of V2 is normal to the surface, okay? Because it's perpendicular to our outer circle. So that means that we can calculate that Vn2 from our volume flow rate. So Vn2, which is that vector right there, or magnitude of that vector at least, is going to be equal to the volume flow rate, which we know, divided by the area of 2. And again, uniform flow assumption, so our area is just a cylinder. Its circumference is twice the radius of the outer edge of the impeller, and its depth is B2, 4 centimeters in this problem. So we know our volume flow rate, and we know this outer area, so we can get that velocity from those two things. So this will be equal to our 1.2633 meters cubed per second. And then divided by the area is 2 pi times the radius, the outer radius, 0.3 meters, and the outer depth, which was 4 centimeters. So that Vn2 works out to 16.755 meters per second. So that's the normal component of this velocity, all right? Next, we need to get its tangential component. In other words, we need to figure out the length of this line right here, from there to there. So basically, we're breaking our velocity up into a normal component here and a tangential component here. Well, the tangential velocity at 2, we can get by taking this total distance, which is R2 omega, and subtracting off this distance. Okay, so that's what we're going to do in this equation. Take our R2 omega minus this part, and that'll give us v tangential 2, which is this bit. Okay, so we start off with r2 omega, and we subtract from that this distance, and we get this distance from this distance, which is our normal component we just figured out, and this angle. Realize this angle is also 30 degrees. So that's going to be equal to Vn2 divided by the tangent of beta 2. All right? So we're after this distance, we know this distance, and we know this angle is 30 degrees. So again, we have the numbers for all of these things. So I'm not going to substitute in the numbers here. R2 is 30 centimeters. Omega is our 2400 RPM. Vn2 is the 16.755 we just figured out. And then this beta 2 is 30 degrees. So all of those numbers go in there. And that gives us a tangential velocity of 46.378 meters per second. All right? So this velocity we're looking for, its tangential component is 46 meters per second, and its normal component is 16.8 meters per second. So from those two, we can calculate alpha next. So alpha is going to be the arctan of Vn2 over Vt2. So the arctangent of the two components that we just figured out. And so we put those two things in there, 16.55 and 46.378, and we get an angle of 19.863 degrees. So the last thing we need to do is to take our two components, the normal and the tangential component, square them, add them up, and take the square root. So again, I'm not going to show that, I'll just give the result. So V2, well, this is our magnitude of the water velocity relative to the ground as it comes off of the outer diameter of the impeller, works out to 49.311. And that's meters per second as well. So just that squared plus this squared, and then the square root of that sum. So 49 meters per second. So it's coming off at 49 meters per second at an angle of 19.9 degrees. So all we need to do is just write our concluding statements, and then we'll also go back and review our list of assumptions. So that's our concluding statement. It tells us the head, the flow, and the power requirements of the pump. The exit velocity is next. So those are our concluding statements. Next, we'll take a look at our assumptions list. So first of all, remember it's a design point calculation, and inherent in a design point calculation is pure radial inflow. So there's no tangential component to the velocity as it enters the impeller. All of the other assumptions that we're going to list are inherent in the development of Euler's equations, which were used for this analysis, and so we'll show those now. So we have uniform inlet and exit, we have a steady state analysis, no heat transfer with the surroundings, the substance is incompressible, and it's operating at constant temperature, right? So those are all the assumptions inherent in the Euler's equations that the analysis was based on. In addition, because it's a design point calculation, pure radial inflow. The one remaining assumption here, of course, is this is frictionless flow. So to get this theoretical maximum efficiency we're talking about, this has to be frictionless flow as well. So that's an example of a design point calculation. I hope you found this useful. If you have questions or comments, please put them in the area below. Thank you very much.